Hi, this is Ferro, and with this presentation, I'm going to introduce the main result of our work titled Adhesively Bonded Joint Brittle Fracture Assessment via Average String Energy Density Criterion. The contents are divided in a brief introduction of the problem and description of the goal to be reached, the analytical frame used to develop the equation that describe the model, results in terms of analytical and experimental comparisons, and finally, as always, the conclusions. Bonded joints have been used for the first time as structural elements in the aeronautical field in 1930. They are today used with the following advantages. They may be strategic in lightweight design, for example, or when thermal and electric isolation must be guaranteed. They are characterized by the absence of distortions. They induce less concentration effects compared to fastening or bolting, and they are suitable for non-metallic materials. Okay, this sounds good, but there are also disadvantages. Maybe one of the most important disadvantages is that a meticulous order and preparations is required. Another important disadvantage is that the designer must take into account the environmental interaction. For example, the working temperature or the contact with solvents. Structural integrity assessment of bonded joint is a formidable challenge, studied a lot in literature. Bonded joints can be treated as B material, characterized by both geometrical, if there's a notch for example, and constitutive discontinuity at the interface between the adhesive and the adherents. Such constitutive discontinuity is due to the variation of elastic material properties at the interface. Both of them, anyway, induce a stress singularity near the point A in this figure. Failure criteria are mainly based on the stress distribution inside the adhesive. One of them is based on the generalized stress intensity factors that quantify the intensity of the asymptotic stress field. However, it is unfortunate that the stress intensity factor parameter requires a very fine mesh near the singularity point and depends on the singularity order, making it impossible to compare the strength of bonded joints with different geometries. In order to overcome these problems, the strain energy density-based approach is proposed for notch components, but not yet applied to bonded joints. So, the goal of the present work is to apply for the first time the average strain energy density approach to bonded joint brittle fracture assessment. In this approach, it is assumed that failures occur when the strain energy density averaged over a control volume or critical radius RC surrounding the singularity point will reach a critical value. For this aim, some hypotheses are required. The first one is that elastic properties of the adherents should be much higher than those of the adhesive. And the second one is that the adhesive should behave like a brittle material, like epoxy for example. Under such conditions, it is assumed that the control volume can be restricted to the adhesive region only, as you can see in this figure. Now I'm gonna to summarize the equations used to formulate the strain energy density in the stress singularity dominated zone. The starting point is the formulation of the strain energy density given by the Beltrami's equation. By substituting the asymptotic stress field in the Beltrami's equation, a new formulation of the energy near the singularity dominated zone is obtained, where lambda is the eigenvalue, f are angular functions, and h0 is the generalized stress intensity factor. Now, by integrating over the contour volume restricted to the adhesive only, as I told you before, and then dividing by the control area, the average strain energy density is obtained. Irrespective of V-notch angle or adhesive thickness, failure will occur when the strain energy density average over a contour volume of radius RC will reach a critical value. In order to obtain the RC value, the energy density to failure of the adhesive only is set equal to that of the adhesively bonded butt joint. In this equation, sigma L is the adhesive stress to failure, while H0C is the critical generalized stress intensity factor that is calculated by numerical simulation, where the nominal strength is obtained by experiments. The geometry of the adhesively bonded butt joint follows that of the standard ISO 6922. In particular, the joint diameter is 15 millimeters, while the adhesive thicknesses modeled are 0.12, 0.4, 2.0, and 7.5 millimeter. This is the mesh used to capture the stress distribution that is shown in the bottom. This table summarizes the critical generalized stress intensity factors values as a function of adhesive thickness and obtained by using the numerical stress to failure of bonded joints found in literature. As expected, unless errors due to numerical approximation or experimental uncertainties, its 0C value is found to be adhesive thickness independent. The mean value is 10.3, and this value was used to calculate the critical radius that is found to be 6.2 multiplied by 10 squared minus 3 millimeter. The analytical value of the strain energy density to failure average over a contour volume of radius RC was compared with experimental values calculated by using a numerical model, the experimental nominal stress to failure as a function of the adhesive thickness. Results are shown in this figure. It is observed a maximum deviation from the theoretical value of about 12% that may be caused by statistical uncertainties related to experimental data. To date, it can be concluded that in first approximation, the critical value of the average strain energy density parameter is adhesive thickness independent and can therefore be used for bonded joint design. So these are the conclusions. The average strain energy density criterion is applied for the first time to adhesively bonded joint brittle fracture assessment. When the elastic properties of the adherents are much higher than those of the adhesive and fracture occurs at the interface adhesive adherents or within the adhesive, the control volume can be restricted to the circular sector belonging to the adhesive only, around the singularity point. By using experimental data coming from literature, the critical radius RC associated to the epoxy steel system was found to be 6.2 multiplied by 10 minus 3 mm. This low value compared to monomaterial system, for example welded joints, is in agreement with the process zone dimensions typical of adhesively bonded joints and represent an intrinsic properties of the big material rather than a mere adhesive properties. And finally, using experimental data found in literature, the energy density to failure average of the contour volume of radius RC was found adhesive thickness independent, proving the validity of the average energy density approach applied to adhesively bonded joint brittle factor assessment. Okay, this is the end of my presentation. I want to thank you for your attention. Bye bye.